Hello. Okay. All right. So where we left off, we talked about the intramolecular forces or dipole. Induced dipole for some isomers of pentane. So now, if we look at the same trend for basically hydrocarbons of increasing molecular weight, we see that as we increase the series here, add more carbon and hydrogen atoms, that we go from the boiling point gets higher in kind of a logarithmic fashion here, or like a polynomial function. You see that? And that's because as we go from, if we look from the top here, as we go increase the number of carbon atoms, we're increasing the linear chain of these carbon atoms. And the longer the chain, the more surface area you can have between molecules, and that increases intermolecular forces. That's why octane is a liquid, whereas methane is a gas, and that's because of the increase in their intermolecular London dispersion forces. Okay. And this is because, the electron cloud around these molecules, they get naturally bigger. And so there are more electrons present. And that causes these dispersion forces to ever so increase because there's more electrons. So now you have more electrons. You can form dipoles that are stronger. And that naturally occurs for molecules with more electrons or with larger electron clouds based on the extended molecule size. Okay? All right. So I will post some more examples about this. So there's a lot of practice. We can get a lot of practice in. Okay? All right. So let's go over this checkpoint here. Arrange the elements in group 8A, so the halogens, in order of increasing dispersion interactions or induced dipole forces. Okay. So remember here we want to consider. So when we're looking at increased dispersion forces, okay, we're going to think about increasing molecular weight. Okay? So the order will be increasing molecular weight. And quite frankly, it's already listed in order. So helium is less than neon, which is less than argon, which is less than krypton, and then it's less than xenon. So this is the trend of increasing molecular weight. And by definition here, the more polarizable you are, you're going to have stronger increased dispersion forces. Okay? So that's how we tackle that kind of problem here. Okay, let's move on. All right, now let's talk about the last type of intermolecular force, and that's called hydrogen bonding. Okay, so the hydrogen bonding is a special type of dipole force that we talked about first, and it's called hydrogen bonding, and that's because it's on a class of its own. Among the dipole interactions, this is the strongest. So they're really strong because they take 15 to 25 kilojoules per mole to break. Okay? So it's kind of a misnomer because hydrogen bonding does not refer to a hydrogen bond within a compound, OH bond. So that's not what hydrogen bonding is. It should be called something else, but we don't call it anything else just because it's an intermolecular force, and just by definition, hydrogen bonding, it kind of sounds different than a hydrogen bond when we say it like that. But I can see where confusion may arise. Okay, so it's this force here pictured in this diagram, the dotted line. So this is hydrogen bonding. Okay. All right. So what causes this type of force? Well, it's due to the polarity of the water molecule. So you see the water molecule here. It's very polar because water is polar. It has a negative pole on the oxygen and a partial positive charge on the hydrogen. And this causes a very strong interaction, okay? It's unusually strong because it shouldn't be this strong. Well, we wouldn't think it'd be this strong, but in nature, that's how it is, okay? And a kind of a real life example of how this bonding takes place is the structure of ice. So ice here is a bunch of water molecules that are hydrogen bonded, and it occurs throughout the structure in solid ice, okay? All right, so this is kind of how nature depicts how water arranges itself in nature as an ice. And you see in the ice molecule, there are a bunch of pores or holes in the structure. So this very ordered structure is weird because in ice is less dense than water, and that's because water likes to orient itself like this in the ice and solid state. So ice has the unique property of being less dense than its liquid counterpart. So usually solids are usually more dense than the liquid form, but in the case of water, it's reversed. Solid ice is less dense than water in the liquid state, and that's why you see when you put ice cubes, water into like your drinks and stuff, it floats because it's less dense than most liquids. Okay, so that's one of the weird properties of water. Okay, if you look at like solid ethanol, it actually sinks to the bottom. So water is this weird exception. Okay. Okay, so what can form hydrogen bonds? Okay, so hydrogen bonds, molecules that can form hydrogen bonds have relatively polar HX bonds, so such as ammonia, water, and HF. So usually these molecules, if they have these kind of bonds here, HF, HN, and HO, these bonds can participate in this hydrogen bonding interaction here. Okay? So the HX bond must be polar to create a partial positive charge on the hydrogen atom that allows this bridging interaction or dipole-dipole interaction to exist. So as the X atom, becomes more electronegative, hydrogen bonding becomes more important, okay? So this interaction is more important when we have the X is N, O, or F atoms, okay? So let's just look at this graph here where we compare the boiling points and melting points due to this hydrogen bonding interactions. So you see here we have HF, H2O, and you see the melting point for H2O is very, very, very high, which is strange because it's the lowest molecular weight molecule out of all of them, except maybe for HF. And you see that the higher molecular weights, sulfur, selenium, tellurium, Cl, Br, and Hi, they have way lower melting points and way lower boiling points on the right. It's even more pronounced for the boiling points. And that's because of this very strong interaction. In the case of water can form two of these interactions per oxygen and hydrogen atom, so it's even more pronounced. So this force is particularly important because it gets some of it kind of makes some of the properties of what water does seem really important, because if it didn't have these properties, water would behave much differently than we know it in the real world, and water is an interesting case. It's a very small molecule. It's very polar, and life without water cannot exist. Okay, so it's a very so much to the properties of water is due to its shape, its polarity, and the fact that it hydrogen bonds and to other molecules. Okay, so this is also what gives proteins their natural structure based on hydrogen bonding within the protein molecules and with water. Okay, so it's water considered an anomaly, and the fact that it does these things, we consider it a universal solvent because it's very good at doing most of these things, that like dissolving things, interacting with things, make why our bodies made most of the water because of its polar nature and stuff like that. Okay, so now let's go into some exercises here. So let's explain why the hydrogen bonds between ammonia molecules are weaker than those between H2O molecules. Okay, so let me just bring up something here. Okay, let's see here. All right. All right. So in this question, we want to think about the electronegativity of oxygen versus nitrogen. So hydrogen. So hydrogen bonds. Between ammonia molecules. Are weaker than those between water molecules. Okay? Because oxygen is more electronegative. So if you put En, that's totally fine with me. More electronegative than nitrogen. So when it's more electronegative, it turns out to be a stronger intermolecular force. Okay? So the reason is this gives a larger partial positive partial charge to the hydrogen. In the OH bond. Okay, so you have a more partial positive charge, the stronger the intermolecular force. Okay? All right. Now let's talk about these molecules here. The following compounds have similar molecular weights. Okay? So let's arrange them in order of increasing boiling point. All right. So these molecules have similar molecular weights. We would expect them to have similar dispersion forces, but these structures indicate that the following intermolecular forces would be present. Okay. So let's arrange them, order of increasing boiling point. So let's talk about each of them. Formaldehyde. So formaldehyde it's polar. So formaldehyde is polar because formaldehyde has a partial positive on the carbon, partial negative on the oxygen. Okay? So it will have polar, it will have dispersion forces. Everything has dispersion forces. Dispersion. It also has dipole-dipole. And then also dipole slash induced dipole forces. All right. Methanol. So methanol is definitely polar, right? It has a polar H here. Oh, sorry, positive here, and also polar oxygen, and well, also this bond here is also partially positive as well. Okay, so it's polar. So it has all the interactions we just listed: dispersion, dipole-dipole, induced dipole, but also another key one is hydrogen bonding. So hydrogen bonding is what pretty much takes the cake here and takes the lead. Hydrogen bonding, okay? Ethane now, there's no electronegativity difference, so this is nonpolar. So anything with just carbon hydrogen, always nonpolar, okay? So this only has dispersion forces. So the least amount of force is present. Well, I wouldn't say that, but the weaker the force that is present, the less, the lower the boiling point will be. Okay. So the order here is ethane is less than formaldehyde. This makes sense, right? Because ethane is a gas, formaldehyde is also a gas, and then methanol is a liquid at room temperature. So methanol, strongest intermolecular force is hydrogen bonding, formaldehyde, dipole-dipole. Then ethane is dispersion. So by that order, it's going to go from ethane, formaldehyde, then methanol. Okay? All right. So let's do these last two examples, and then we'll call it good for this lecture, okay? All right, so let's arrange the following compounds in order of increasing boiling point. All right. So these have very different molecular weights. So these had similar molecular weights. These have very different molecular weights. So we're going to say different. And then some of these compounds are polar and some of them are not polar. Okay? So when they're very different in weights, you want to consider their dispersion forces, or the force that's dependent on molecular weight. Okay? So when you have different molecular weight, you want to think about the dispersion forces, or the total number of electrons based on the increasing molecular weight. Okay, so we would predict that boiling point should increase with an increase in molecular weight. Okay? because this will have increased dispersion forces. Okay. So let's just write the molecular weights of each compound. So tetrabromobutane, or the molecule of 4 bromine atoms, has a molecular weight of 373.6 grams. So very high. And then carbon tetrachloride is the next. It has 154 grams per mole. And then acetone has the least, which is 58 grams per mole. So by this, the logic of increasing molecular weight for more or stronger intermolecular forces, we're going to say that tetrabromobutane will have the highest. So we're going to say C4H6, Br4, will be the largest boiling point, so it's going to be greater than the carbon tetrachloride, which is greater than acetone, which has the lowest boiling point. Okay, so that's our prediction there, based on the molecular weight. Okay, so we should be able to predict that based on if something has similar molecular weight or different molecular weight. In this case, we're going to go with the dispersion forces, even though one has different intermolecular forces. If there are different molecular weights, we have to consider the dispersion forces as being the most dominant determinant of the boiling point. Okay? Now let's do the last example where we arrange the following compounds in order of decreasing boiling point. Okay? So these molecules, they have similar molecular weights if you kind of think about it. This has 8 carbon atoms, C8. This is C10, decane. And this is nonane, this is C9. So they have very similar molecular weights. Okay? So their molecular weights are between 142 to 144 grams per mole. So very similar molecular weights here. So in this case, now we have to determine each of the compounds' molecular intermolecular forces to determine which one has the higher boiling point. Okay. So if we think about these structures, only one of them has hydrogen bonding. Okay. All right, so let's look at octanoic acid. So let's erase this. Don't need that no more. So octanoic acid. So it's polar. And it has a lot of these intermolecular forces here. It has hydrogen bonding. So this one is the only one capable of having hydrogen bonding. So that one should be the highest, I would think. And then the next one is dipole, induced dipole. And then dispersion forces. So decane, though, is nonpolar and only has dispersion forces. Okay. Now nonanol is polar, but it does not have hydrogen bonding. So nonanol, the CHO is this. So imagine this R group is the carbon atoms, and then this has a C, double bond O, but the H isn't attached to the oxygen, it's attached to the carbon. So no hydrogen bonding here. But it's still polar because of the carbonyl, or the C double bond O. So it's still polar. And it still has dipole interactions. And it still has dipole-induced dipole. And it still has dispersion forces. However, it does not have hydrogen bonding, and that's what makes the difference here. So octanoic acid, the carboxylic acid, will be first. And then decane is not polar, only has dispersion forces, so it's going to be the weakest because it will have the lowest boiling point because all these compounds are of similar molecular weight. So this time we consider the strongest IMF to determine the trend in boiling point. So in this case, we're going to say I guess I didn't. Did I? Okay, I think I did this backwards. So let's go back a bit. So it said increasing boiling point. So in this case, we have to arrange it differently. So we're going to say C3H6O is less than CCl4. And because in this way, it's increasing boiling point. And this will be the bromine. C4H6. Br4. And this one, we're going to do decreasing boiling point. We're going to say octanoic acid is greater than nonanal, which is greater than decane. So this is decreasing boiling point. Okay? All right, so that's it for this lecture. We'll pick up in the next lecture more about intermolecular forces, and then we'll wrap up this semester of chemistry talking about more about solutions. Okay? So I'll see everyone next time.